Okay.
Rosie says we're live.
Good evening, everyone. Thank you for joining us on our festive edition of Astronomy on Off Tap, Edinburgh. My name is Shinran, and as many of you know, Astronomy on Tap is a free event run by volunteers. And that's obvious this evening since we had some fun technical difficulties at the start, but we're here with you. And traditionally, many of you know, we take over a local pub and to share and discuss science over a few or many pints. But since lockdown started, we have moved our events virtually online. So you will have to bring your own drinks, but you can still learn about awesome science from the comfort of your own home. The extra great news is that we have an awesome lineup for you tonight. As our last virtual event of 2020, we have a slight change of format as we will be finishing with a festive game between our speakers. So speakers, you've been warned. I've been told by our resident games master the game tonight will require pen and paper, so please have them handy. If you have a moment, please subscribe to our YouTube channel and follow us on Twitter and Facebook. It would help us a lot. And if you have any questions throughout tonight's event, just pop it in the YouTube chat or via any of our social media channels, and we will ask the speakers your questions after their talks. If there is a topic you'd like to learn more about, or indeed is an expert on, we'd love to hear from you. So just, again, message us via our social media channels, and we will endeavor to get back to you promptly. So without any further ado, let's start. And firstly, it's over to our resident rocket man, Fred, who is going to give us an update on the exciting happenings in the world of rocket launches. So please sit back, drinks at the ready, and enjoy. Over to you, Fred.
Hi, Jinran. Can you hear me okay?
Yeah.
Right, I'm going to share my screen.
You seem to become a satellite. I love it.
It's pretty cool, eh? All right. Can you see that okay?
Yes, perfect.
Hold on. Need to F5.
It needs to go into present mode, I think.
Yeah. Now it's stuck. Hold on. Let me try that again.
The festive gremlins have really invaded our tech department this time.
There we go. My F5 isn't working, but I'll carry on anyway.
Okay. I think you can go into view and then full show slides or something.
There we go. Can you see that okay?
I still see the same screen, but I think it's fine. Yeah, we can still see your slides.
Okay, hold on. I'm having trouble changing between the pictures now. Let me try that one more time. Okay, how's that?
Yep, looks good.
Right. Sorry about that. Yeah, so welcome to the rocket launches for December 2020. So first up, I just want to mention that the Chinese Chang'e 5 moon lander landed successfully and should have departed with its 2 kilograms of lunar rocks and things. Because we spoke about this last month. This was a future launch. Okay, next up is, this has already happened, 2nd of December, Russia's launched 3 comm satellites on the Soyuz 2, which is pretty cool. And then 5th of December, Dragon cargo supply mission CRS-21 unmanned would have gone to the ISS, and I was launching a payload which is called the Bishop, which is a new airlock for the Tranquility node. And there's a bunch of other stuff on the payload as well, but it takes too long to talk about it. Next up, SpaceX launched an XM7 for a new startup company, which is British, and its digital audio radio service. Next up, 10th of December, China's GCAM, which is a gravitational wave high energy electromagnetic counterpart all sky monitor mission. That's a mouthful, and it's launched on a Long March 11. That's quite a suite of cool rockets that the Chinese have. And then 11th of December, China's second Angara A5 test, which being a second tester for the new booster that's fully made within Russia. December 12th, Japan's Strix synthetic aperture radar satellite launched on a Vega booster, which is a Ariane European rocket. Next up, December 14th, India's CMS-1. It's to provide tele education, telemedicine, disaster management support. And that's being launched on the Polar satellite launch vehicle, the C-50. Next up, December 16th, NASA's Cygnus CRS-14 to depart from the ISS. And then on December 17th, Russia's OneWeb 4. It's for a high-speed internet. This one's particularly interesting because the Russians are introducing a policy of responsible space policy, which means that everything will deorbit within 5 years so you don't get clutter building up. And that's launched on a Soyuz STB rocket. And then this one, Virgin Orbit's ELA-20, is to launch nanosatellites, but this is being launched from a 747 on the Launcher 1. So that's pretty cool as well. Thank you. Hope I got all of them, didn't miss any.
Oh, well, that was awesome. Thank you, Fred. I'm amazed to see so many launches planned for this time of the year. All right, perfect. Now we're going to move to the first guest speaker of the night, who is Dr. Aaron Celestian, who currently researches how minerals interact with their environments and with living things, and how those minerals can be used to solve problems like climate change, pollution, and disease. Dr. Celestian is the curator of mineral sciences at the Natural History Museum of Los Angeles and an associate professor at the University of Southern California. And he is affiliated research scientist at NASA's Jet Propulsion Lab. And we are all super excited for him joining us tonight. So over to you, Aaron.
Great. Well, thank you very much for inviting me. This is really a pleasure. Let me share my screen here and present. Hopefully you all can see that. And so away we go. So a lot of my work is looking at mineralogy and looking at how bacteria on Earth are trapped within mineralogy and how that could be used for analogs for looking at life on other planets. So I only have 10 minutes here to talk to you, so I'm really gonna go kind of quickly and not into a whole lot of detail, but we're looking at salts, and that's one of the main minerals, these various types of salts that I'm really interested in working in. And on the main picture here, you see that this is a halite crystal. This is just regular table salt, sodium chloride, and it's pink because there's all kinds of a molecule called beta carotene that's trapped within the crystal structure, trapped within the crystal. And also there's a lot of bacteria trapped within the crystal as well. So this process is happening on Earth, and I'll show that in a little bit more detail next. So what we're gonna look at in these crystals, am I starting at the beginning? No, I'm not, sorry. Okay, here we go. So what we're gonna look at is we're gonna assume some habitable environments on Earth. And this is one of them. This is a place called Cyril's Lake. It's just in Southern California in the United States. And the water is pink because there's all kinds of halobacteria, bacteria that like to live in super, super salty water. And they have to release this chemical, this beta carotene, as a sunscreen to protect themselves from just intense ultraviolet radiation. So eventually this lake is this water, this is a bird's eye view of this water, is gonna dry up and it's gonna form crystals. Those crystals will have beta carotene trapped in them. So this was a science fair project my son and I did for his school a few years ago. He's 10 years old, so it's a really simple science fair project. And we took waters from different lakes, the Great Salt Lake in Utah, and also Cyril's like from Trona, California, and you evaporate the waters in the petri dish. And the idea is like, where do these bacteria go? Where do these beta carotenes go? Do they just, as the crystals grow, do the beta carotene just coat the bottom of the petri dish, or do they actually go, and most of them go inside the crystal? And you can see on one on the right, that has lots of beta carotene, is that you can see through the bottom of the petri dish, and it's not very pink stained, but most of the pink is stuck within the crystals. So the idea here is that as the crystals are growing, even if there's just trace amounts of bacteria or beta carotene, they're going to find their way into the crystal. Now, what is the water chemistry like? What is the mineralogy, water interaction going on? That's what I'm mainly interested in, and how that happens. But there's lots of different types of salts. Halite is just one type of salts. That's any crystal that's evaporating, that forms from evaporating liquid. Table salt is one of them. This is that same crystal again. And again, you can see nice cubic crystals that form the nice halite crystals. There's also halite. This is from Poland. The green color in this case doesn't come from bacteria. It comes from another mineral that's included inside of it, a copper chloride mineral. And then here's another crystal. This is from Arizona, where it's just crystal clear. But it has a little bit of purple and blue, and that purple and blue comes from radiation damage within it. So all these halite crystals can come in a wide range of colors. So it's really important to understand what the color is telling you. Is it bacteria, beta carotene, or is it some other process? But there's other salts. There's mirabilite, which is a sodium sulfate salt, and it's not stable on the surface of the Earth. This is a crystal I grew in the lab at pretty close to 0 degrees Celsius, just a few degrees above it. And it's stable under very, very cold conditions. But as soon as I took this crystal out of the water to take the photograph, this is a photograph of it right away as I took it out of the water, it converts to another mineral called thenardite. So thenardite is stable on the surface of the Earth. Mirabilite really isn't, unless it's super cold. But just because it's not stable on Earth doesn't mean it doesn't mean that it can't be stable on other planets in moons. So we're looking at a variety of salts, all that encompass what we think might be found on other moons and other planets in our solar system. So let's take a look at life and how it looks like inside of these crystals. So a lot of these halobacteria, that's what we're really looking for. On the left-hand side, you can see is these rod-like beasties that have little wiggly things at the back of them. I'm not a biologist, so excuse the terminology. But after they get stuck inside of the crystal, they change shape. They get into these more round shapes of the image on the cartoon image on the right. And they can stay like this for who knows how long. In fact, we really don't know how long these bacteria could persist in this state of hibernation. There's crystals from Mexico, the Cave of Swords in Mexico. The 50,000-year-old bacteria have been recovered from it. There's other indications of million-year-old bacteria coming from them. There's ecosystems that are millions of years old that have been separated from surface processes that have bacteria still persisting in them. So they can live for eons. So, and that's one of the reasons why we're still looking forward to them. So here's a crystal that we grew in the lab. This is a halite crystal. And we wanted to see, where does the bacteria go? Where does the beta carotene go? And can we see them without even cracking open the crystal? And so if we take a look and we zoom in a little bit more, you can see that now you can start to see these like diagonal rectangular pockets within the crystal. And these are fluids that are trapped during the crystallization process. If we take even a closer look at it, you can see that now there's these at the tips here, where you see these fluids that are trapped in. They're pink in color, and that's where the beta carotene is. So not only is the crystal stained with these beta carotene molecules that are produced by bacteria, but they're trapped within the fluids with the bacteria itself. Now, if we zoom in even further, let's say we zoom in on one of the fluids, what we'll see is bacteria just kind of floating around within it. So each one of those little tiny dots is a 1 micrometer bacteria that's stuck inside of the crystal. And they are just kind of swimming around and doing their thing. We need to take a look at another fluid inclusion within the crystal. See that now there's a whole bunch of these bacteria. So sometimes you find one, sometimes you find several thousand bacteria still swimming around in these crystals. So they can live for long periods of time. They are protecting themselves from ultraviolet radiation, which is important if you go to look for them on Mars, because Mars has a pretty high UV flux on its surface. So if life were to live there, it needs to have evolved something to protect themselves from ultraviolet radiation. Maybe it's beta carotene, maybe not, maybe it's something else, but you need to look for some of these biosignature chemicals. But we're also looking in the deep Earth as well. So the surface of Earth is just a tiny, tiny fraction of what is around the surface of Mars. That's what we're mainly probing. But there's things that are living in the deep Earth as well. This is me in the Balby mine, northeast part of England by Whitby. And here I'm close to a mile underground. This is salt that's Permian in age, which is about 250 million years old. And on the left is a crystal that I recovered. It's got fluid inclusions in it, and it also has bacteria within the crystals as well. So that begs the question, are those bacteria 250 million years old? Or is there other geologic processes that are happening that we just don't know about that brought in bacteria from someplace else? So unfortunately, we're still doing the DNA work on that with my colleagues at JPL, but hopefully we'll have an answer soon at some point. And you can see these fluid inclusions and other minerals stuck within the crystal. So on Mars, well, we have evidence from past missions of Mars. We have evidence that water is present on Mars. There's also salty places on Mars as well. This is just a series of animations of reoccurring slope lineae, which is just a fancy term for water seeping into the ground and staining it. And this is a series of images that go through the summer, and you can see that there's streaks developing in the soil. And this happens annually. And so there might be hidden aquifers, there might be some mineral reactions that are releasing water into the soil and then later on being reabsorbed. We don't know, but satellite spectroscopy shows that these places are quite salty as well. So now we have salty environments, we have potential places for water, even possibly surface water on the surface of Mars. The only thing we don't have is find evidence of life. And that's where the next mission, that's where Mars 2020 is going to go to. It's going to go to Jezero Crater and look for it. And that's where Jezero Crater is indicated on the map there. And it's possibly an ancient lake bed that had water in it. And it has this, on the right-hand side, is a false color image showing different mineralogy. The green colors are clay minerals from water weathering processes. And it has the same delta structure, like water, fluvial dynamics and fluvial processes that are happening as like an Earth-like delta. So similar geomorphology is what we'd call it, similar geological properties. And an artist's rendition of what that looks like might look like this, where you have this lake and you have stream coming in, water building up, and then you have some outflow areas. So really good place for having potential liquid water, potential salt crystals that might be harboring life, might be found at Jezero Crater. So with that super fast talk, I'd like to turn it over to the host. Thank you.
Awesome. Thank you so much, Aaron, for that fascinating talk. And so much covered in so little time. We have a few questions from our audience. So first of all, the question is, are you able to detect life in samples if we were to find such minerals in comets such as Rosetta? So if you found some minerals in a comet, would you be able to search for life there?
Yeah, and that's one of the things that I didn't get a chance to talk about, was that we are developing the techniques where you can look for signs of life optically in spectroscopy without ever having to open up the crystal. So as soon as you open up the crystal and you start extracting things out, then you're introducing contamination and other issues like that. So we're trying to develop techniques that where you can look inside the crystal spectroscopically, get as much information as you can before you open up the crystal and start extracting out organic molecules. So yeah, that's really the hope, is to have this more holistic approach to analysis. But you need more than just one type of, you need more than just looking for beta carotenes. You need multiple lines of evidence to really prove life is there, and that's a monumental task.
It actually answers one of the other questions we had as well. Another question is there anything usable from the return of the Japanese comet mission?
There potentially are. And that's really interesting, looking at icy moons and possible life on Europa and Enceladus. Who knows that there could be these icy places where life has accumulated in other parts of the solar system as well. So it's unknown. I'm usually optimistic about these things. I'm not too optimistic about the comet. Places like Enceladus and Europa have active geology taking place that could provide the necessary heat and nutrients for life. So we'll see, but it's definitely worth looking into for sure.
Actually, I had a follow-up question from that. So I mean, we met at the Bobby Underground Lab when you were searching for life in the salt crystals there that have been underground for 230 million years or something, as you said. So you found life in those salt crystals. So are they just surviving in these micro pockets of nutrient-dense pockets inside the salt mineral, or how are they, or like as in between different pockets of bacteria, are there any way that they can communicate or talk to each other? Well, not talk, but
yeah. So these fluids are not those. I showed like the little square block of fluid that was in the crystal, and over time those fluids can migrate, and they might migrate because of some kind of geochemistry that might be happening within the pocket itself. So if life is consuming salt or changing the chemistry of the fluid, then that would dissolve part of the crystal and then recrystallize part of the crystal on the other side. So you can have like a salt kind of moving, or salt pocket of fluid kind of marching its way through the crystal. That's definitely been observed to happen. If that's happening down there in Balbi, I don't know off the top of my head. But those are things that we're looking for. I hope that question.
I had another question, which is, how hopeful are you about finding life in those Martian crystals?
I'm pretty hopeful. If there was, of course I am. I wouldn't be doing it if I was super negative about it. I'm pretty hopeful. It seems like the conditions were right. It seems like there was enough water, that there was potentially enough heat and potentially enough nutrients. Now, there hasn't been water on the surface of Mars for 3.5-ish billion years. So there'd have to be some sort of other process there to help them persist for that long a period of time. I am optimistic about the recurrent slope lineae. There's also deep Earth processes, deep Martian processes as well that could help provide nutrients and provide energy. But we won't know until we get the samples back, but I'm optimistic.
Awesome. Just last question. Does the composition of the crystal change over time? And if so, does that affect the life of affect the bacteria that lives in it?
It could. So in the case of mirabolites, some of these really unstable salts, water can leave the crystal structure completely. And as you saw, it went from a nice clear mirabolite crystal to an opaque thenardite crystal. That would be really bad to happen if life was in that, because that means the whole entire crystal structure is broken down, its protective coffin is totally disintegrated, and then it would just be left out into the environment to decompose. So yeah, you'd have to, mostly it's the water issue that we're really concerned about. But any process that changes the chemistry could potentially break apart the crystal because of stresses and strains on the crystal, and that would be detrimental.
Cool. Well, thank you so much for that amazing talk. And so please stay with us, as I think we have a festive game for you at the end. But in the meantime, we are moving to our resident games master, John. I can't wait to hear what game you'll be bringing us this month. Looking forward to it.
Hi, Jinran. So I'm just going to share my screen now, if you bear with me 1 second. Okay, so hopefully everybody can see my screen. Jinran, is that showing up okay?
Yep, looking good.
Okay, great. So good evening, everybody. So I'm the resident games master for tonight's event. As you can see, this is a very obvious, clearly Christmassy game. Look at the Christmassy lights. There's a hat. It's very Christmas related. All you're going to need for this game is a pencil or pen and a bit of paper, or if you draw on your phone, tablet, Etch-a-Sketch, if you want to write it in bubbles on the side of a wall, finger painting, all of this is allowed. So essentially what you'll need is just some sort of drawing implement and then some kind of tool to use for that drawing implement. So that's all you need. So if everybody could go and grab one of those just now, and once you've got that, I will start. So bear with me 1 second. Okay.
got my pen and paper at the ready.
You got it ready? Okay, so essentially this game is called Drawing Conclusions. And what this game is essentially I am going to give you some instructions for drawing a picture. And this picture is going to be a basic picture. I will be able to see this picture and nobody else will be able to see it. So this is the name of the game. I cannot tell you shapes. I can't say, draw a circle, add a triangle on top of it. I can only give you directions as to how to draw this. So I will give you directions on where on the paper, on what kind of lines you need to draw, how far, but I won't be able to give you specific instructions about how you can do this. So all I need to do is give you instructions about how you draw it, when you draw it, and then at the end, we'll compare what the picture looks like to what you actually have drawn. So if you've got your pen and paper ready, if you've got your implements, once you've drawn it, once you've finished, please do share it on Twitter, stick it on Facebook, let us know, send us a picture of it, and then we will try and show some of those ones at the very end of the event today and compare them to how they should be looking. So if you bear with me 1 second, I'll just get my picture up. Okay. So for this picture, what I will need you to do, right in the center of your page, I would like you to draw a square. So a square, not straight up, just on its side. So I'd like you to draw a square that looks like a small diamond. Right in the middle of your page, draw a small diamond shape. And then once you've drawn your diamond with equal sides, I want you to go to the right of your picture, and I need you to draw a second diamond. So going upwards from the right-hand side, I would like you to draw a second diamond, so they are next to each other. Draw the two diamonds next to each other, and the left side, the bottom left sides, those two are parallel to each other. So there is two small diamonds with the point up and point down, and they are next to each other going up towards the top right-hand corner. Two small diamonds in the middle of the page. Hopefully you're with me so far. Every time we've done this activity in different environments and different events, it's always come up with some truly terrible, terrible pictures. So I'm hoping this works again this time as well. So right now you should have two diamonds somewhere in the center of your page, and they should be going upwards towards the top right-hand corner, and they should be parallel on the top right side. Now, in between of those two diamonds, I would like you to go to the bottom right side, so going down to the bottom right corner, and I would like you to draw a large square, which is about I would say, about 1.5 times those diamonds you've drawn. So this is to the right-hand side, going down to the bottom right corner, diagonally down. So you're going to draw a large square there, similar in shape to the two diamonds you've drawn. And I would like you to draw it next to those two. So you're going down towards the bottom right-hand corner. So it's a large square. Once you've drawn that one, then draw it to make it into 4 quadrants. So you need to draw a line down it, and a line going down between it, so it has 4 quadrants. So essentially it looks a bit like, I'm cheating here, a bit like a window, okay? That's not a clue at all. Okay, so once you've drawn that, go to the other side, so going up towards the top left-hand corner, next to your two diamonds in the middle, and draw another square on its side, similar to the two diamonds, and again, do 4 windows, okay? So you need to do 1 on the right-hand side, 1 on the left-hand side of the diamonds, either side, and it will be split into 4, okay? Both squares, okay? All right, so right now, should be 2 diamonds in the middle. To the right-hand side, there is a square with 4 quadrants. To the left-hand side, there is a square with 4 quadrants. Now, at the bottom, so go down to the bottom left-hand corner, on your bottom diamond, as you've got that side that's looking down to the bottom left-hand corner, draw a small, tiny triangle connected to your bottom diamond, a small, tiny triangle. And then connected to that, do a half circle, okay? So the half circle connects to that rectangle that you've just drawn, that tiny one. The bottom half of the circle connects to it, and then it's a half circle, so it's cut in two. Okay. This is going to go spectacularly wrong, I hope, because it's funnier that way. Once you have done that, then from your small oval, your half oval, draw a triangle going down, pointing down. So the point of the triangle points down to the bottom left. And so that goes out from your oval. Draw the small triangle going down to the bottom left. And then at the tip of that triangle, draw 3 concentric lines that go in ovals. So the tip of the triangle has a concentric line going across the top of it. It looks like an oval. And the next one, and the next one. So there should be 3 going outwards. They should get progressively bigger. So it should go 1, 2, 3 lines, all parallel, all concentric, going outwards. Okay? All right. So that is your drawing. That explanation was interesting. I'm sure you all agree. But hopefully you have a picture somewhere. Everybody has some picture that they've put on their paper. Please take a picture of it, screenshot it, put it on Twitter, AoT_EDI. Please put it on Twitter so we can see it. And then at the end, I will show you the actual picture and also what you've drawn as well. So thank you, everybody. I'll pass back to you, Jinran.
Thank you very much. I'm not sure why Drew makes any sense to anybody, but I shall take a photo of that and share. All right. So in the meantime, whilst you work on your masterpieces, it's over to our next speaker, who is Dr. John Davies, who is an astronomer and aerospace engineer at the UK Astronomy Technology Centre in Edinburgh. He has worked on fighter jets, astronomy satellites, and ground-based telescopes. But his main scientific interests are asteroids and comets. Today, he is here to tell us about some of the consequences from the advent of the thousands of satellites in low Earth orbit, which promises to access of internet from anywhere and everywhere on Earth. So over to you, John. Tell us something about that.
Right, okay. I'll just do the screen share thing. Yeah, my name is John Davies. I actually predate the space age. I just mentioned that because I'm told this is for young people. I still think of myself as young. Chronologically, I may not be. Okay, so internet, satellite constellations, the new vermin of the skies. So my first question is, where does that word come from? Where does that expression come from? Well, I'm interested in asteroids. And when astrophotography started, when people first started taking long time exposures of the night sky in around about the turn of the last century, so around about 1900, many of the photographs were spoiled because what you see, because of what happens on the left-hand side of the screen here, that a moving object, in this case an asteroid, passes through the field of view and draws a streak on it. This is a near-Earth asteroid as it happens, but the effect is the same on long exposure photographs of deep sky objects. And so many of these asteroids were actually discovered this way, but so many of them destroyed people's photographs that many astronomers started referring to these things as the vermin of the sky because they mucked up all of these astrophotographs. But today,
John, sorry to interrupt. Are you sharing some screen? If you're sharing a screen at the moment, we can't see it.
All right, my mistake. Yeah, thank you.
No problem. It seems like the festive gremlins are.
Oh, you're right. No, it's an operational problem at my end. You're right. I got to share the screen, haven't I? I know how to do this. Come on. Share screen. There we go. Share. Now I do the slideshow thing. Okay, so now I hope you can see something that says once upon a time.
Yes, perfect.
Okay, so thank you for that. So once upon a time, 100 years ago, people were taking photographs of the night sky, finding little streaks in them, which were asteroids, small rocky objects in the solar system, orbiting mostly in a belt between Mars and Jupiter. And they became called the vermin of the skies because they were messing up people's photographs. Today, we have another problem, and that's illustrated on the right. And that is that from time to time, at least, your photographs can be ruined not by one, but by many streaks which fly through it during the exposure. And these are satellites. Now, the first satellites were essentially one-offs, or launched in very small numbers anyway. Only a total of 9,000 have been launched in the entire history of the space race. But in more recent years, since about the year 2000, there's been a move towards satellite constellations. And one of the most famous of these is this, it's the so-called Iridium constellation. The Iridium satellite program was a first attempt to get mobile phone coverage over the whole of the Earth's surface. But in order to keep the power requirements of the mobile phone low, these things have to operate from low Earth orbit. And if you're in low Earth orbit, the satellites move across the sky very quickly, so you need lots of them. So the original plan was to have 77 individual satellites, each of which would be visible from somewhere on the Earth. So if you were anywhere on the Earth, you'll be able to see at least one Iridium satellite. You could talk to the satellite. In a few minutes, it would disappear, but that was okay because by then another one would have come over the horizon. And the reason they were called Iridium is the original plan was to have 77 satellites, and 77 is the atomic number of iridium. So in some sense, the Earth was the nucleus and the satellites were the electrons going around this iridium atom. Now, this in fact turns out to be not a viable business model, and the original Iridium business went bust. It was taken over and reinvented itself as a specialist broadcaster for people who really need coverage all over the world, like television broadcasters, but it was never a success as a mobile phone platform. It also was the first of these things to produce big issues for astronomers because of the shape of the satellites, they could occasionally catch the sun and make a very bright flash of light projected down onto the ground, and these became known as iridium flares. People briefly thought they might be some new astronomical phenomenon, but it was quickly tracked down that they were just glints of these iridium satellites. But iridium's not the only satellite constellation. Another one which you may be familiar with is the Navstar satellite system, which makes the global positioning system. Now, Navstar has 24 satellites in 6 orbital planes this time, and they work. I don't know if you ever thought about how GPS actually works, but it works because each satellite is essentially constantly shouting, I am satellite 12, my position is such and such, and the time is 1 o'clock. And your little widget in your car or in your phone gets these messages, but because the speed of light is finite, it takes a few microseconds for the signals to get down to your phone, and your phone can quickly work out that it's a slightly different distance from satellite 12 as it is from satellite 17 than it is from satellite 24. And so it uses this time delay to calculate the distances to the satellites and then triangulate to get the position of your phone on the Earth's surface. So in the case of GPS, Navstar, time delay actually makes them work. But this time delay, which is a function of the physical speed of light and which you can't change, creates an effect called latency. And latency is the time delay between a signal being sent and it being received. And you've all seen it. You've probably seen it on Zoom. You may have seen it on Zoom tonight, or on international live TV broadcasts where both people start speaking at the same time. Then they both stop speaking at the same time. And that's because of the time lag in the signal. Now, you can't do anything about the speed of light. So if you put your internet relay satellites up in the geostationary orbit where the big TV broadcast satellites sit, the latency is going to be 477 milliseconds. That's an eternity for an internet system. If you want to have reliable broadband internet anywhere on the Earth, you need much lower latency than that, and you can't operate from geostationary orbit. Your solution is you have to have thousands of satellites in low Earth orbit. You need thousands of them because each one's only visible for a few minutes before it flies overhead. And as they disappear towards the horizon, they may disappear behind mountains and things. And you need to have them in orbits that go right from the equator to the pole. So you need thousands of these things. The latency in these low Earth orbits, a few hundred kilometers, is only 25 microseconds. So it's 10 times less than, it's 10, 20 times less than you would get in geostationary orbit. So these Starlink satellites, however, are not that small. I mean, when we think of large numbers of satellites, we tend to think of CubeSats, but actually these Starlink satellites are quite big. They're about the size of a tabletop, 1 meter by 3 meters on the flat bit. And then they have a solar panel that sticks up, which can be, when it's deployed, is of the order of 13 meters. So these are quite big things. They each weigh about 220 kilograms. And they all potentially reflect light back down to the Earth. There's another constellation as well. We heard about that in the presentation about this month's rocket launches, which is OneWeb. OneWeb satellites are a bit smaller than Starlink's, a bit lighter than Starlink's, but they operate a bit higher up. The original constellation plan is for 650 OneWeb satellites. There's of order 1,000 Starlink satellites planned, but OneWeb have a request with the Communications Commission to launch up to 48,000 of these low Earth orbit satellites. And these are potentially a big problem for us astronomers, because this is what happens. This is the dark energy camera of the Sierra Tele into America's observatory. They're taking a picture, and suddenly this whole fleet of satellites flies through, completely messing up the image. Now, the main problems when these satellites is soon after launch, when these satellites are close together in the sky and quite bright, but they remain a problem even when they reach their operational orbits. Luckily, it's not all bad news, because it's mostly a twilight thing. Now, you don't have to worry too much about this graph. The top third shows the number of satellites which are above the horizon from a particular observatory in the summer, and the answer is 1,000 of them. Luckily, most of them you can't actually see because the sun's not shining on them. And the blue line, the sort of turquoisey blue line, is the number of satellites which are not only above the horizon, but it actually has the sun shining of them. Because these things reflect light. If they disappear into the Earth's shadow, they vanish. The colored bars off to the edges of the white section in the section, in the center, are the twilight zones. So the sun goes down, then you have civil twilight, nautical twilight, and astronomical twilight. And as you get into astronomical twilight, the Starlink satellites start to disappear because they're quite close to the Earth. So when the sun sets for you on the ground, it sets on the satellites not much later. And you can see that after an hour or so after sunset, most of these satellites aren't illuminated. And it actually gets better than that, because most astronomers don't look at the horizon. They look at altitudes above 30 degrees. And the bottom panel shows that the number of satellites visible above 30 degrees drops off to very small numbers within an hour of astronomical twilight. So, unless this is the worst case, this is in the summer when the sun is relatively low below the horizon, so the satellites stay illuminated for longer. In the winter, when the sun dips below the horizon much more quickly, the situation's even better. So at first sight, it doesn't seem too bad, but it's very dependent on the altitude of satellites. These are the Starlinks, which are relatively low. The same graph for the OneWeb satellites, which operate at about twice the altitude of Starlink, is much less encouraging. In this case, even above 30 degrees, there are still hundreds of satellites visible at midnight. And that's because they're sufficiently high that they can still see the sun, even though it's long set on you and your observatory. So this is potentially a big problem, although it's mostly a problem for people who like to observe near the horizon in the twilight. Most astronomers prefer to observe directly overhead and in the middle of the night. But there are some things which are best observed in twilight, and this is one of them. This is a comet, and this is a comet, and it's actually made up of several short exposures which have been co-added by this chap, whose name's down in the left-hand corner. But you can see that there's a huge number of satellite trails right across this image. Now, you know, arguably it's completely destroyed the image, although it's quite an interesting image by itself. You can also see a little meteor trail, I think, there, and a regular satellite flung across in the background. But there are a number of projects which are potentially threatened by these satellite constellations, and those are projects which need to look near the horizon, such as comets, because comets are almost brightest when they're near the sun, so you only ever see them near the horizon. Near Earth asteroids, they're sort of things that could actually kill you by landing on your head. These are often most easily detected by twilight observing, and that's when these streaks on the asteroids are going to get lost in streaks on the satellites. And then you get these transient phenomena like gamma ray bursts and gravity wave events, which happen and don't last very long. And when you get triggered, you have to go and look for it. And you can't just say, well, we'll wait a couple of hours till they tire up, because in a couple of hours it'll be gone. So these satellite constellations do represent a potential threat to certain kinds of astronomy. Some are relatively immune, narrow field observation, spectroscopy in small fields, not so much of a problem. Wide field imaging, and there are several large wide field imaging telescopes being built right now. The Vera Rubin Observatory is planned to map the whole sky virtually every couple of days, and that could be seriously impacted by these satellites. Now, luckily, the satellite operators are reasonably alert to this. The Starlink people have engaged with the astronomy community and tried to think about ways of minimizing this problem. They have two strategies. One is called DarkSat, where they've literally painted the satellite or tried to paint the antenna a lower emissivity material, so they're not so reflective. So even though they're pointing down at the ground, they're not so reflective, so they don't shine quite so brightly. And the second one is this thing called VisorSat. Now, this image is, I think, actually slightly unrealistic because it's sort of upside down. The bit that reflects down on the Earth are the white bits that you can see in the top of the picture. So really, the satellite should be upside down, and those bits should be pointing to the Earth. And what Starlink have done is they've built these things with little pop-up sunshades, which pop up once it's in position. And then these stop the sunlight falling on the antenna and thus stop the reflection back down to the Earth. So that makes hopefully will make these VisorSats somewhat less obtrusive to astronomy. So that's one solution, is you just hide the satellites by either painting them black or building in shades to them so that they don't glint in the sunlight. From the ground, if you know exactly when the satellites are coming, and that's a problem in itself, but if you know exactly when they're coming and you're taking the long exposure picture, you could perhaps close your camera shutter for a few milliseconds or a second or so while the satellite flies overhead, and then start your exposure again. But if you've got a very wide field of view, you're going to have lots of satellites impacting you, and you'll be going to be constantly shuttering and then reopening your camera. Software fixes, well, we know how to remove trails from images, but these satellites are so close to the Earth that they're actually slightly out of focus. So they're not like solid bars of light that are easy to subtract with an algorithm. And they will create extra background noise, which will make it hard to detect faint objects. I say not all projects are affected by this. It depends on precisely what you're trying to do. But the ultimate question is, what's the night sky worth? Some people would argue that astronomers, this is just special pleading by astronomers who want to keep the sky for themselves at the expense of everybody else. Other people are somewhat, more generous. My own, question you've got to ask yourself is, how much is a dark sky worth? I mean, we all, how much is it worth to have a dark sky which doesn't have satellite trails in it? Now, if these satellites are providing genuine broadband internet connectivity over the whole world, and they can save lives because they can inform farmers, they can educate people, they can be used for telemedicine and that sort of thing, then that's great. That's a price worth paying. If, on the other hand, the main user is wealthy young people in rich countries who haven't got anything better to do than play networked games of Minecraft or something, then you might think, well, maybe that's not a justification for ruining the night sky. And it's not just people like me, astronomers, who care about these things. The night sky is important to lots of people, amateur astronomers, people who are interested in the sky from a spiritual sense, who might want to go out and look at the night sky without being interested in the science, but then suddenly a bunch of bright satellites fly across it. And that's a judgment that we all have to make. How much is a dark sky worth? I don't have the answer to that. I'll leave that as a question for the audience, so to say. And that's me. I hope that made sense, and I hope it gives you some idea of the problem we're dealing with. It's not the end of the world, but I think cooperation between the astronomers and the satellite developers will be important if we're going to solve this problem in the long run.
Thank you so much, John. That was fascinating. We had lots of questions for you there. Just to start, I think we had a question from the audience that's saying, are you saying that geostationary system will replace the current GPS satellites? And is that in order, and would that help to reduce space pollution? Will these satellites address the problem of space junk?
No. Okay, so no. The geostationary orbit, the 24-hour orbit where the satellites remain essentially hanging in the sky directly above, in the same spot on the sky, they're used for big communication satellites and for television direct broadcast satellites. So they're not so good for the internet, because the time it takes a signal to get up to them and the time it takes a signal to get down again produces this latency problem. The GPS system is completely different. That's a positioning thing, which is just using the latency as a way of measuring the distance to the satellite. These low Earth orbit internet comms are a third type of thing, and they're designed to provide rapid communications without any latency for broadband. So they're three completely different classes of objects, and none of them replace the other. They're three quite different things.
Mm-hmm. I had a question, was how reliable are the 22 kilogram solar panels, and are they easy to fix?
Well, you don't, I mean, the solar panels, you don't fix these. The Starlink satellites and the OneWeb satellites are mass produced literally many a week, and you wouldn't bother to repair it. You just let it break and then launch another one. And that's another issue for the whole light pollution thing, which is that the satellites are mostly a problem on their way up while they're still close to Earth and just been launched. But in order to have a population of thousands, many of which will fail, you have to keep launching them to replace them. So it's not a problem where you have a couple of years of lots of traffic and then it goes away, because there's going to have to be constant replenishment of these constellations. So we're going to have lots and lots of things going up, for the foreseeable future, as long as these networks are operational. So they don't fix them. They just let them fail and then send another one to replace it.
Actually, that links nicely to the next question. Is there a record of satellites that are out of use, or and what happens to them when they no longer are functional?
Well, it depends on the height. The stuff that in very low Earth orbit will decay naturally, because the atmosphere kind of puffs up and down, creates drag, and satellites re-enter. Once you get above about 1,000 kilometers, though, these orbits are stable for 1 million years. So I worked on a satellite in 1983, which stopped working in late 1983, and will still be up there in thousands of years, and still be up there for thousands of years, because it's high enough that there's no atmospheric drag. And one of the things which we'll need to do with these constellations is to find a way of deorbiting them once they reach the end of their life. In fact, that video which I started showing you and then stopped is actually showing the collision of an Iridium satellite with a Soviet Cosmos satellite, which creates a huge cloud of debris. The debris is a whole different problem to deal with these things.
Yeah, for sure. And just the last question, is there a critical mass of satellites? Like, what is there a number needed to go up before we can't really do any observation, or are we already quite close to that?
Truthfully, we the astronomers are still thinking about this. It's only really become an issue in the last year or two, and a lot of people are spending a lot of time modeling the satellite populations to try and figure out what the danger, what the risk is to observations, how observation will be affected. and other astronomers are actually making real observations of the real Starlink satellites to measure how bright they actually are. Because at the moment we're doing a lot of calculating and guessing and statistics, but we need some real data to say, well, actually the dark sat is half a magnitude fainter than the regular Starlinks, and the visor sat is half a magnitude fainter again, or whatever the numbers are. So we can feed that to the designers and the operators and say, this is the best thing for our to solve our particular problem. But it's not just our problem. I mean, astronomers don't own the sky. Sky belongs to everyone. And we've got to look at lots of different people's points of view.
Of course. Actually, sorry, just one last question. The question is, what frequency does this affect? Is it only the visible light that affects?
That is a good question. And the answer is it's not actually just visible. I mean, there's a problem for optical astronomers because of these bright trails you get in our photographs. But an even bigger problem is actually for radio astronomers, because the radio astronomers are worried that these vast amounts of electronic signals which the satellites are beaming back to Earth will have side lobes and leak into other frequency bands where radio astronomers want to work. As an optical astronomer, I'm primarily concerned with the optical aspects, but I do know people who are working on the radio aspects, and in fact, they, I think, are more worried than we are that radio contamination will be a really big problem for radio astronomers.
Well, thank you so much, John. I think if people have more questions, we'll send them over and then try to post them back to the audience. But thank you so much for that talk. And finally, since it's Christmas, we have one last game, which will pit our speakers against each other in a friendly way, of course. And for this, I hand you back to our resident games master, John.
Good evening again, everybody. So, as Jim says, we do have one last game that we are going to be taking part on. So, for this game, our speakers are going to be involved. I will share my screen just quickly to show the rules of this game. For anybody who was brought up in the UK, this is based around a TV show called Mallet's Mallet that was hosted by Timmy Mallet way back in the halcyon days of the 1990s when I was a wee nipper. And it's basically a game where you have a subject. Two people will have to think of words related to that subject. For example, I could say dinner, and then you could say lasagna, spaghetti, plate, spoon, and it goes back and forth until one person's mind, from all the terrible pressure of being live on the internet whilst talking, goes blank, and that person is out. And so the other person is the winner. So essentially, if I just share my screen quickly, if you bear with me a second. So this game, appropriately for AOT, is called Space Off. So I can't remember the name of the mallet. I think his name was Mallet. I might be wrong. But this is Space Off, the Christmas edition, hence the Christmas hat. Two speakers enter, one speaker leaves. A little bit of a Mad Max reference there. So the rules, and I'll explain this. Okay, so the name of the game is, I don't have a large foam mallet or a Hawaiian shirt or that good haircut, so I can't really do this. But the name of the game is, yes, again, there is a subject, and the rules are that you have to think of words associated with that subject and then say them. So two players come in, which are our speakers tonight, who've kindly agreed / press gang to be into playing this. You'll be given a category. You take it in turns to name a word associated with that. No hesitating, repeating, or randomly going off topic. And I am the judge of that. And I'm incredibly impartial. So don't worry about that. And then the winner is the person who is the last man standing. So those are the rules. So if I can ask our speakers to unmute and turn on their videos. Okay, so, okay, Aaron, are you ready for this?
I'm ready.
Great, hold on, I will just change the screen around. Bear with me 1 second. Okay, so Aaron, you're ready, great. John, are you ready for this?
Ready is too strong a word, but you may proceed.
Okay, all right, so I'm just going to see if we can arrange us, I think, okay, right. So what I'm going to do is I'm going to quickly share my screen for both of you one more time, just to show you the topic. Then I'll give you just a couple of seconds to think, to let your brain sort of process what you're going to be doing, and then I will start. Is that okay with you both?
Okay.
Okay. Yep. Thumbs up from John. Great. Okay. So let me go through this again. So the first category for the first round will be things you'd find on a space shuttle. Things you would find on a space shuttle. Okay. I'm just going to stop sharing my screen for a minute. Okay, so who would like to go first? Aaron, you have 2 A's at the start of your name, so you are alphabetically dominant here, I would say. Sorry, John. But so Aaron, I will allow you to go first. You have the subject, things you would find on a space shuttle. Go.
Window.
Window. Toilet.
Rocket.
Rocket.
Remote manipulator system.
That is very specific. I love it. Okay, keep going. Aaron.
Antenna.
Antenna.
Inertial navigation system.
Oh, that's fantastic. Okay, back to Aaron.
Door.
Door.
Radiator.
Radiator.
Computer.
Computer.
Orbital maneuvering system.
Fantastic.
A chair.
Keep going.
Fin.
Calculator.
Oof, that was close, but I'll keep going, John.
Reaction control system.
Oh, very good. Back to you, Aaron.
I don't know. I'm stuck.
Oh, I'm afraid I'll have to count you out there. John, that was so many adjectives. I've never seen that many adjectives outside of a thesaurus. That was a fantastic game. Well done, well done. Aaron, I apologize, but I have to declare John the winner of round one.
Yeah, well, I'm a bit of a space freak.
All right, well, don't worry. There are 2 extra rounds. We'll go through them quickly. I'll just reshare my screen. So that was round 1. Round 2. Plenty of time to make up in here. So round 2 is TV shows either in or about space. So this could be a TV show that's about space. I won't give you examples, that's cheating. Or it could be set in space, but it has to be a TV show. Okay, I'll give you a second to think about it. And I will stop sharing my screen. Okay, John, as the round 1 winner, I will allow you the Nobel thing to go first. Are you ready?
Yep.
Okay, John, go. TV shows in space.
Fireball XL5.
Very good. Aaron.
Star Trek.
John.
Lost in Space.
Aaron.
Mandalorian.
Very good. John.
Battlestar Galactica.
Good news. Aaron.
Man, TV shows in space.
Oh, I think I've counted you out. I was going to give you time. That was a tough one.
Yeah.
I will say we did do this live when we used to have our when we were on tap in pubs, and somebody had the very clever idea of we did films set in space, and we went through every Star Trek film that's ever been done.
Yeah, well, my next answer was going to be Battlestar Galactica reboot.
So you could. Those are additions. Those are allowable. I should have been probably more clear with the rules. So. John, you win round 2, and so we have 3 rounds, but you've won 2 out of 3. We will do the 3rd round just for, I made the slide, so I'm proud of it. So hold on. This one is a slightly easier one. I will give you this. Okay, Aaron, this is your chance to get your consolation round. So 3rd round, very space related, Christmas decorations. Now specifically decorations. I will be very strict on this, Christmas decorations. So Aaron, we're back to you as the start for this one. So Christmas decorations, go.
Tree lights.
Great.
Baubles.
Baubles, good job.
The star tree topper.
Yep.
Yeah, the fairy on top of the Christmas tree.
Right, I'll allow it. It's a differential.
Stockings.
Very good.
I hate Christmas. I give up.
Oh, you're good night, John.
If my wife was here, we'd still be going in an hour's time to decorate the Christmas trees, but it's not really my thing.
Oh, well, I must say that you both were fantastic, and thank you both for playing, because it isn't easy to be thrown into a game live on YouTube, but you were both brilliant. So thank you so much for playing. I have to announce that our winner is John. Congratulations. Well done, John. You're the inaugural winner, but thank you for playing as well, Aaron. Okay, so I'm just going to very quickly, before I hand back to Jinran, before we stop, I'm just going to announce the results of our game earlier. We did have a few contestants sharing their pictures. So I'm just going to very quickly share my screen and show everybody. Bear with me 1 second. Okay, so, oh no, wait, that's the wrong one. Bear with me. We've just done that one. Let's try that again. Okay, so for our drawing conclusions game, so we had some entries, and so I'll go through those first, and then I will show you what you should have been drawing. So we had some interesting ones. Here was our first attempt. Now this one, I'm not sure what happened here. There were very clear instructions. I think they might have just been playing Tetris while they were doing this. I'm not quite sure what it is. Second one, which you'll see later, but I was very impressed with. Third entry, again, this one was very, almost perfectly spot on. And our fourth entry, again, very close, a little bit kitey, but I still liked it. So what you were actually drawing, which you must have guessed by now, was a satellite that did not look like this. This is the last entry. Looks like this. So actually, almost everybody got close, apart from that first entry. But that was very impressive. So congratulations, everybody. Thank you so much for sending in your pictures. And well done. And I'll pass back to our host, Jinran.
That's amazing. I love the competition round and those entries. Absolutely. I gotta admit, I was totally lost after the first like 5 instructions. But well, amazing. Thank you so much, John, for another awesome edition of games. And all that's left for me to do, I think, is on behalf of the Astronomy on Tap or Off Tap team here at Edinburgh, I would like to thank our awesome speakers again and our audience for tuning in and for staying with us as we tackled our festive gremlins. I think someone's definitely be feeding them a Christmas feast after midnight, since it's a fun December treat. But all that's left for me to say then is have a fantastic Christmas and a great new year. And I'm happy to announce that we will be back. So we will all see you in 2021.